Alright, hi. So I actually have no idea when I'm gonna post this video, but I'm recording this on August 19th and 2021. I mean, I really don't think I would post this any later than 1 year from now, but it is 2021 right now. Anyway, a couple of days ago for my time, because I'm probably gonna upload this a couple of weeks later realistically, I made an announcement video basically talking about my summer and basically discussing that I'm at an internship right now with an electronics company for the science research program at my school. I'll just leave a link to that video if you don't know what I'm talking about or you haven't seen it, because I really don't feel like explaining that all right now. So basically, yes, this is a gaming channel, but technically in my channel banner, I say that I also post other stuff. This can be that other stuff. So I want to start posting electronics videos on this channel, and I cannot stress this enough. I am an 11th grader, not even. I have basically no education in electrical engineering. I mean, besides just reading articles and things like that. But electrical engineering is actually my dream major in college. That's what I hope to get into. And in the science research program at my school, of course, I'm studying electronics. Now, of course, I'm still learning for sure. I really only know some pretty basic components of electricity, or some basic principles of electricity. So I'm not sure if I am gonna post electronics videos on this channel. Maybe this will be the only one that I ever post, but we'll see. If you like this type of content, I'll definitely make more, because electronics is, once again, a topic that I'm very interested in, and I want to learn more myself and also maybe share my knowledge along the way by making electronics videos. So this idea literally just completely randomly came into my mind. So I used to have a model railroad, which I destroyed. Actually, I don't know, that's a long story. I'm not going into that. I mean, I still have it. It's just sitting like in a bag actually in the hallway out there. But for some reason, a lot of my friends thought that touching the tracks, because model railroads are actually electrified. Alright, hi, this is Light from the future, and for some reason what I said next didn't make it into a video clip. I don't know if I forgot to record or if I accidentally deleted it, but I'm just gonna reiterate what I said next in this clip right here. Model railroads are electrified, and the way trains on a model railroad actually move around is from voltage from a power supply being delivered to the actual two tracks. I meant to say rails on the model railroad. It's a little bit similar to how third rail works on real trains, except third rail has an actual separate third rail that's electrified, while model railroads are electrified from the actual two main steel rails they run on. The trucks of the trains, or basically like the wheels, are conductive, so the DC motors in the train are sensitive to voltage and voltage changes, and you regulate the voltage of the power supply or the controller. So depending on how much voltage you give to the steel rails, that'll change the speed of the motor, and that's essentially how model railroads work. DC model railroads, actually. There's a difference between DC and DCC, but I'm not going to get into that right now. A long time ago, when my friends would come to my house and I actually had the model railroad set up in my room, they would be afraid to go near the model railroad because they're like, oh, if I step on it or if I touch it, it's going to shock me, or oh, it can kill me maybe because it's electricity. Literally, none of my friends have brought that up in at least like 5 months or so, but it just randomly came on my mind. So let's debunk why touching a model railroad won't kill you. And this is a video that I can actually make because essentially this relies on simple electronics principles. Little disclaimer here. Once again, I am only an 11th grader. I am not an electrical engineer. I do not have any degrees or certifications or anything, obviously, so please don't take advice from me 100%, okay? I don't think I'm gonna explain concepts in this video like 100%, and especially probably not 100% accurately, but I'm gonna try to explain as much as I can because, again, the goal of this video is to essentially show that model railroads are safe, and the power supply of model railroads are safe as well. And I'll also try to briefly explain some concepts of electricity. So this right here is a power supply, or actually this is a controller for the model railroad, but in reality this is essentially just a power supply. This is how you can control the speed of the model railroad, and this is a DC model railroad, not a DCC. So basically changing the voltage of the tracks will change the speed of the train because it'll just change the voltage. It'll just make the DC motor in the train run at different speeds by changing the voltage. I'm pretty sure the maximum output voltage on this thing is 12 volts, and you can regulate it. This is like a throttle controller. That's what they label it as. Like it has like 5, 10, 15. It has all of these increments over here. But you can see this is 0 volts, and this would be 12 volts here, and somewhere here this would probably be like 6. Now, before I get into anything else, I want to explain one very fundamental part about electronics, and probably the most fundamental equation in electricity, and that is Ohm's law. And Ohm's law states voltage is equal to current times resistance. But first of all, what's the difference between current and resistance? And voltage. Well, I'm probably not going to explain this very well, but voltage is essentially potential energy. I said potential energy. I don't know why the video made it sound like I said tensile energy. That's required for electricity to flow, and current is essentially the actual movement of the electricity. You need potential energy in order to have, like, actual kinetic energy. The best way I can describe it is through an analogy of, not necessarily a very pleasant one, but an analogy about a gun and a bullet. So voltage would be the actual speed of the bullet that the gun provides, and current would be the actual bullet itself. So a bullet can't injure anyone if it's just staying still. So at any amount of current, if you have no voltage, the current is not going to run through your body and kill you because you have no voltage, you have no potential energy. That's just like holding a bullet. Holding a bullet is not going to do anything. But if you have high voltage, which is basically like your bullet going 100 miles an hour, of course that's going to injure you. Oh, and then you also have another thing, which is resistance, which is pretty easy to understand. It's your own resistance from electrical current. Well, I don't know why I said your own. It's a conductor's, or your own as well, because your body has its own resistances. Actually, literally anything's resistance to electricity. Different parts of your body have different resistances, and it's not the 100% exact same for everybody. Typically, your skin and your fingers have a much higher resistances than, let's say, your tongue. So, like, 6 or 7 months ago, something like that, I posted a video on LightningRandomContent of me licking a 9-volt battery. Now, if you lick a 9-volt battery, you'll actually be able to feel the electricity because the resistance of your tongue is very low typically. But let's say if you apply a 9-volt battery to literally your fingers, you just put a 9-volt battery here, you're not really gonna feel anything at all because the resistance of your skin is very high, which limits the amount of current that can actually travel through your body. And yes, there is actual current flowing when you touch a 9-volt battery. It's just less current because you have a higher resistance on your skin. And once again, Ohm's law is voltage equals resistance times current. And if you use simple algebra, you can rewrite it. Like if you want to calculate for current, you can just divide by resistance on both sides to get current on its own side of the equation. So that means voltage divided by resistance equals current. There are a ton of other electrical formulas, which I'm not going to get into, and I don't know a lot of them. But equations and formulas are very fundamental in electronics. Okay, I know this definitely isn't the greatest angle down here, but it's something. At least you can actually see the power supply. So, see, I am going to plug it in. So basically the way this power supply works, or train controller as what it's used for, but you can see it has an on and off switch. If I turn it on, it's on because it is plugged in. You also have a direction lever. Switch, not lever. I call a lot of things lever in this video for some reason when I don't mean to say lever. And this is just for the direction of the train on the model railroad. So if I turn the power supply on and I move this all the way up here, you can see it's running on 12 volts now, and this is about 6 volts and 0 volts. And of course, there is no actual voltage setting here. It just goes on increments of 5, 10, 15, 20, just to indicate like the speed of the trains, because that's what this is designed to be. Now, remember the rant I went on earlier. This is a maximum of 12 volts here. If you touch 12 volts with your skin, you're probably not even going to be able to feel it. You may feel it like a little tiny bits. The resistance of your skin is very high, and the voltage is relatively low. 12 volts is relatively low. So no catastrophic amount of current is going to go through your body from 12 volts. Voltage is not the only factor in electronics that matters. It's resistance as well. And the resistance of your skin is very high. So that limits the amount of current that can flow through your body. I'm going to take these two cables, and these cables are connected to the power supply, and what you would do with these cables in a model railroad is you would actually put tracks between these cables, like railroad tracks between these cables, and that's how power would be delivered to the actual tracks. The tracks themselves would be electrified, and the wheels of the train are conductive, so that's how the motors of the trains actually get power. Kind of similar to third rail and real trains, except third rail and real trains doesn't electrify the actual steel rails. It electrifies that one third rail on the side. Okay, so you can see the power supply is on, and I'm gonna put it on 12 volts. Also, don't try dangerous things at home with electricity. Only do things if you know what you're doing, please. So between these two contacts, there are 12 volts here, and you can see I can actually short them, and you can see some actual sparks as well. What I'm gonna do now is I'm gonna put my hand on one and put my hand on the other. Look at that. I'm touching it, but again, I'm gonna do this again, right? You see, I'm touching them. This is 12 volts right here. So my body right now is at 12 volts, but the actual current flowing through my body is limited because of my skin's resistance. This is exactly what would happen if you actually touch a model railroad. Literally, I'm closing the circuit right now. This is a 12 volt power supply. This is on full, and I'm touching it like this. This would not kill you, okay? So hopefully this is debunked for you now. I can actually probably power something with this right now. If you want me to, I can still debunk it more and actually power stuff. Actually, before I do that, I'm gonna take some measurements with my multimeter. This is actually future light again, and I actually forgot to power something like I said I would in the video. So I'm actually gonna do that right now. So this is a 100 microfarad electrolytic capacitor rated for 50 volts. And if you don't know what any of that means, that's fine for now. Basically, if you don't know what a capacitor is, this can hold electrical charge, and it charges when it has power, but it discharges as soon as power is cut off. Yes, capacitors discharge when power is cut off, but they also need a load or something to actually power, like an LED, let's say. Capacitors are actually quite similar to batteries, but they're more temporary. And when it discharges, components in the circuit will actually have power for a couple of seconds until the capacitor finishes discharging. And depending on the capacitance of the capacitor, it will be able to hold more charge or less charge. And in this case, this is 100 microfarads, which is not really a lot. When this capacitor discharges, the actual circuit will not have power for all that long, probably like 3 seconds, and it'll actually get dimmer. Not even 3 seconds, like half a second, literally. 100 microfarads really isn't a lot. And it'll actually start losing power very frequently. You'll see what I mean. Also, if you've seen any video of electronics parts exploding, I can guarantee you've seen an electrolytic capacitor explode. They do not take reverse polarity well. Not all capacitors are polarized, but electrolytic capacitors like this one are. Let's just hope I get my polarities right. Okay, we're back to this setup, and as you can see, I have a breadboard over here, and on this breadboard, I have an LED. It would also be smart to get a resistor. Hold on. Okay, I got a 330 ohm resistor. I'm not gonna get into circuits and how to calculate resistance or any of that. If you're interested, I can definitely do that in a future video. Okay, I have this 330 ohm resistor attached to the anode of this LED. So I have no power source right here, but I'm gonna charge the capacitor with the model railroad controller while holding it and showing you that the LED will turn on and the capacitor will discharge through the LED. You can see that this capacitor is not charged. You can see the LED, and even if it was, it would discharge right now. Actually, for safety, I'm gonna get my multimeter out, and you haven't seen the multimeter in the video yet, but sneak peek, this is my multimeter. Now, on this power supply, you can't tell what's positive and negative because it switches with this direction switch over here. So there's no easy way to tell except for measuring it and basically trial and error. I'm just attaching the probes of the power supply. Probes of the multimeter, I meant. To the actual two contacts on the model railroad, and yep, this is negative right here. So this is the wrong way. Now if I just flip the direction of the two, let's just make sure this is positive. Yes, okay. You can see we have positive voltage in here. Negative is all the way on the left right here, so all the way to the bottom. I just gotta remember that. But if I flip the direction, it just changes the polarity of the two contacts. So if I keep it in this orientation, I'm gonna charge this to about 6 volts. Not charge, you don't charge power supplies. I meant to say something like power. No, maybe like 9. I'll do like 9 because I have a 300 ohm resistor. So that should limit the current enough so it doesn't blow my LED. Yes, I could have charged the capacitor to like 2 or 3 volts, so I don't even need a resistor, but higher voltage demonstrates my point better. Now, obviously the model railroad controller doesn't have any gauges. I have to use my multimeter to check, and even then this multimeter is not the most accurate thing, as you'll see later on in the video. That's actually exactly 9 volts. This is my capacitor over here, and I separated the legs for safety purposes. Not safety, well, yes, safety, so it doesn't short. You can see the shorter leg of the capacitor is the cathode or the negative end, and the longer is the anode or the positive end. I'm gonna turn on my power supply. So my power supply is set to 9 volts right now, and you can see if I take the two contacts, I can actually short them and you can see some sparks. I don't know how well you can see it, but there are some arcs there. Okay, so we gotta remember the negative is over here. This is the negative end. I am going to take my capacitor and take this probe over here of the power supply, and I'm going to attach it to the negative end of the capacitor. And I'm also gonna touch it. I'm touching it. Now I'm gonna take the positive end. So first of all, right now, you can see how I am literally touching both ends of the power supply. So now I'm gonna put positive end here. This is 9 volts right here, and the capacitor is charging. And I'm holding both the capacitor and the power supply right now. So the capacitor only takes like a second to charge, literally. I held it there for a very generous amount of time. So now I'm gonna turn off the power supply. I'm gonna make sure not to short the capacitor. Okay, there you go, put the legs closer together. Well, of course, the best thing happened here. My phone died and the footage didn't save, so I actually need to repeat this again, but I'll do it quickly. Okay, I definitely need to make this quick because I have to go to my internship today. It's actually the morning, it's like 8:20, something like that, and I have to start getting ready in like 5 minutes. Okay, so I remember the negative was over here, but I just want to double check real quick. Better to be safe and not mess with reverse polarity on capacitors. And let's see. Yes, positive 9 volts over here. Okay, once again, you can see I can touch them, no problem. I can short them. It's on. Okay, so now I'm gonna charge the capacitor again. See, I'll separate the legs. Okay, see, negative is in here, holding it. Positive is gonna go here. You can see I'm also holding it. Okay, it's definitely charged at this point. Gonna put the legs closer together without shorting it. And now, this is the part of the video that you haven't seen. You're gonna turn off the power supply. I am going to put the capacitor into the breadboard over here, and you should see for about a split second, this LED will turn on, and I'll actually turn the light off so you can see that better. Okay, so I put the anode or the positive end of the LED in the breadboard, and once I put the cathode or the negative end in, you should be able to see the LED turn on. And that means that the capacitor was indeed charging, and what I was holding there was live voltage. There you go. I think you saw that. The LED just turned on for that split second. All right, enjoy the multimeter voltage measurements. So this is my multimeter right here, and this is a cheap one. I got this for 10 bucks. Literally, 10 bucks on Black Friday on Amazon. This is not very great, definitely not very accurate, but it gets the job done. This thing is terrible for measuring current. I mean, to be fair, all multimeters are terrible for measuring current. Yeah, my project that I'm doing at the internship has stuff to do with measuring current, but I'm not gonna get into that because confidentiality stuff. So I'm actually gonna attach these probes to the two. So I'm gonna hook up these two probes to the power supply and show that there are 12 volts there. Okay, we're back at this angle again, and you can see the power supply is running and it's on its full 12 volts. You can see these are the two contacts. I can touch them. And again, I can short these and you can see actual sparks there. Oh, I think I'm actually burning it. Oh. So I'm actually going to turn the power supply off for this, and you can see I have my multimeter. I'm going to turn on the lights. I don't know if you can see it, but I'll actually just read the voltages out loud. That's on the screen. You can see I'm going to attach one end of the probe to here. And I'm gonna attach the other end to here. So you can see right now this is at 0 volts, and this is a manual range multimeter. So right now I'm in the 20 volt range. So this can go up to 20 volts here, measure it relatively accurately. I mean, this is not a very accurate multimeter itself, but for what it is. So you can see right now 0 volts. As I increase this lever over here on the power supply, look at that, the voltage goes up 3.16 volts. You can see it's negative just because this is polarized and I connected the probes backwards, but it doesn't matter for the purposes of this. You can see I put it up here. This is probably like around 6, something like that. 7, wow. Wait, hold up. What happens if I put it on max? Wait, 16 volts? Wow, I thought this was limited to 12, not 16, wow. But you can see how inaccurate this thing is. It keeps jumping back and forth, but you can see a peak of 16 volts here. Yeah, so you can see there's real voltage here that I'm actually measuring with my multimeter. I'm just gonna flip the direction of the probes just to make it not negative. If the timeline of this video isn't confusing enough, it's August 25th, and I'm actually planning on posting this video for the Friday premiere of this week. And the last day of my internship should be tomorrow if everything goes according to plan. That's kind of irrelevant to this video, but I thought I would just say that anyway. What I wanted to say here is I didn't necessarily need to flip the direction of the probes. I could have just flipped the direction switch, because this is a model railroad controller, flipping that direction switch will literally just reverse the polarities. That's why there is no clearly labeled positive or negative on the actual power supply. Depending on what setting the direction switch is on, positive and negative will vary. So essentially you just need to test it with a multimeter to check the voltage to see if it's positive or negative. If it's negative, then you connected it backwards, but if it's positive, you connected it correctly for the current configuration of the direction switch, if that made sense. Real power supplies would not have a direction switch because they don't power model railroads, and you don't need to flip the direction of the train, and real power supplies would also make polarities very obvious. You would never have to question it. There you go. Now you see it's just a regular 16 volts. 16.45 volts. And I can touch it. I don't know how well you can see it. You see, I'm touching 16 volts with my fingers here. Also, I never really mentioned this in the video, but typically you feel DC less than AC, and this is DC here. And I emphasized this before, if you don't know what you're doing, please do not mess with anything. If you don't feel comfortable doing something with electronics, then you probably shouldn't do it. Also, the resistance of people's skin is going to be different, and the resistance of your own skin is going to vary, like, in different places as well. Also, if your skin is, like, wet or something like that, that'll actually decrease the resistance. So there are factors that can decrease the resistance of your skin. I'm pretty sure fingers tend to be a little bit higher resistance than the rest of your body. Also, there could be like some other factors or something that I'm literally just not aware of that can influence how much current you can actually feel or how much current will actually flow through your body if you touch voltage, or touch a voltage source rather. I don't know why the screen of this thing gets dim. This is not a great multimeter, but it gets the job done. So essentially, that's all I wanted to prove in this video. Model railroads will not kill you. And at the same time, we learned something about the basic principles of electricity and Ohm's law. Once again, some things I said in this video may not 100% be accurate because, again, I don't have certifications and I'm just a kid. But I think it's nice to share my knowledge, and if you found this video interesting and you actually want to see more electronics video on this channel, definitely let me know because I'll happily make more. Maybe I'll also get a legitimate power supply at some point as opposed to this model railroad controller, but it'll do for now. This model railroad controller and a 9-volt battery are essentially the only power supplies I have. I mean, a 9-volt battery is actually considered a power supply. Anything that can actually supply voltage is considered a power supply, essentially. Thank you for watching. I actually decided to make this sporadically, but I think it was a good idea. I had fun making this, so thank you for watching, and goodbye.